Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. As we were discussing in the last lecture, the friction part, right. So, and we have seen that how we can draw the free body diagram of the different components which are involved to develop some frictional force, right. If you look at, so in the last lecture we showed this figure, right. So, if you look at block A, so these are the forces are acting on block A, fine. So, this F basically we are now going to find out, and you know how to find out that force, but just for sake of completeness we are going to discuss this friction, and I hope you are quite familiar to this force friction. Okay. And then similarly you can draw the free body diagram of surface B in such a way that these are the forces are acting on surface B. Okay. So, now if there is no relative motion, because what we are doing here, we are trying to pull this block A over the surface B, but immediately it will not, I mean, see this T force, you are gradually increasing this T force, and you will observe at certain point the block will on the verge of sliding, right. Till then there was no relative motion between A and B, right. Why? Because you are applying some force T, so the block A immediately will slide, right, but that is not happening actually. Why it is not happening? Because the frictional force, that is F force, is trying to resist that kind of relative motion, right. So, if there is no relative motion, then the static friction force can be given as Fs equal to T, right. So, Fs, that is your static friction force, is equal to T as long as your T, that is the pull out force, that is the pulling force, is equal to your static friction force F S, you will not be getting any relative motion of the block A, right. And the static friction force can be obtained as you know, where Fs is nothing but your static coefficient of friction. Okay, that is your static coefficient of friction. These are the things are quite known to you anyway, and N is the normal force as shown in this figure. Okay. So, what I mean to say, as long as your T, because you are gradually increasing the T, right. So, in the process up to a point when T is equal to your static friction force Fs, there is no relative motion. Immediately the T crosses this Fs, then you will be getting the motion, right. The block will try to slide over surface B. Okay. So, that kind of situation happens. So, your relative motion is possible if your T becomes greater than your Fs. As long as T is equal to Fs, there is no relative motion, but once T crosses this limit, then basically you will be getting the relative motion, and at that time your body A will be sliding over the surface B, as you know, and that is defined by your kinetic friction force. right. So, that is known as your kinetic friction force, and this is your kinetic friction coefficient. Okay. Or kinetic coefficient of friction. So, this way basically the movement initiates, right. So, initially you will not be getting any movement, and suddenly I mean as your T is going on increasing. So, basically you will be getting this condition, and finally the kinetic friction will govern the movement. Okay. So, now there are few properties of this frictional force we should know. Okay. Few inherent properties of this frictional force. What are those? The first property is that both coefficients means static friction coefficient as well as kinetic friction coefficient. Okay. Both coefficients of friction are nearly independent of the area of the interface. What does it mean? The first property says that both coefficients of friction are nearly independent of the area of the interface. What does it mean? Suppose in the plan view, suppose this is one surface and this is a block, say block A. You are trying to pull this block A with a force T, and on the same surface you are taking another block which is really bigger than block A, and you are trying to pull this block with a force T, and both the blocks are giving same amount of reaction force N. N is same for both the blocks, block A as well as block B. What is N? As already you have seen in the previous figure, that N is the reaction, vertical reaction at the surface or at the interface, right. So, now both the blocks are providing me same amount of N. If they are providing me same amount of N, then basically from the figure it is clear that A is much smaller than block B, that is area wise, but that will not affect the friction force which is getting developed at the interface. Okay. So, this friction force, as we have told here, that both the coefficients of friction, static coefficient as well as kinetic coefficient, are nearly independent of the area of the interface. So, now for block, as long as block A and block B both are giving same amount or both are generating same amount of N, okay. So, the friction force are not getting affected, or friction force is completely independent of the surface area, okay, the area on which the block is resting. Okay. Now, the next property is both coefficients are nearly independent of the roughness of the two surfaces. Okay. So, the friction force is not dependent on the roughness of the surface. So, people have, or people generally have a very wrong impression that if you have very rough surface it will give me higher friction. It is not. Okay. The friction force is independent of your roughness of the surface. That is the next property. Next property is Fs, that is the static coefficient of friction, is nearly independent of the time of contact of the surface at rest. Okay. Fs is nearly independent of the time of contact, okay, of the surface at rest. So, at rest condition, I mean how much time the block A is resting on the surface B, it is not giving any kind of say dependency on friction, okay, or friction is not getting affected by the time of contact between block A and surface B. Okay. That you can see from this figure. If you come back to this figure, you will see that this is your static coefficient of friction, okay, and this is your time of contact between two surfaces, and you see that this variation is like this. Okay. So, this is a variation. So, it is almost clear that the Fs is independent of your time of contact. Okay. Now, next point is Fk, that is kinetic coefficient of friction, is nearly independent of the relative velocity of the two surfaces. Okay. Fk is nearly independent of the relative velocity of the two surfaces. So, it does not depend on the relative velocity. That means relative velocity means if your B is stationary, if the B surface is stationary, if the A is moving, right. So, there is some relative velocity getting developed between these two bodies, but that Fk is completely independent, okay, of the relative velocity. Now, that you can see from this figure. If you come back to this figure, you will see that this is your Fk, that is the coefficient, kinetic coefficient of friction, and this is the sliding velocity. Okay. So, as I mean once your kinetic friction is getting developed, at that time it does not depend on the velocity of the sliding block. Okay. So, as you can see, it is merely independent. Okay. Fine. So, now this Fs and Fk, therefore, we can say Fs and Fk are intrinsic properties of the interface between the two surfaces. Okay. So, finally, we can conclude, or we can say, or we can see that Fs and Fk, that is a static friction as well as kinetic friction, both are intrinsic properties of the interface between the two surfaces. Okay. So, that is the intrinsic properties of the interface. Interface means block A and block B both are having some common surface, right. That is that interface is I mean the intrinsic properties of that interface will govern Fs and Fk. Okay. So, now we will take some numerical problems to understand whatever we have discussed so far in this particular chapter. So, let us take this numerical problem. Problem says the simple triangular frame shown in figure is used to support a small chain hoist. Find the forces acting on the wall at B and C when the chain hoist is supporting its rated capacity of 20 kilonewton. The members BD and CD are pinned at their respective ends. Okay. The figure is looking like this. Okay. So, this is the problem. What the problem says? The simple triangular frame as shown in the figure is used to support a small chain hoist. Okay. This is a small chain hoist. Okay. Find the forces acting on the wall. So, wall is here. So, this frame is basically mounted on a wall at B and C when the chain hoist is supporting its rated capacity of 20 kilonewton as shown in the figure. The members BC and CD are pinned as shown here. So, these are all pin joints, okay, frictionless pin joints, and you know what is the speciality of pin joints, okay, at their respective end. So, what are the things you have to find out? Find the forces acting on the wall at B and C. So, you need to find out the reactions developed at point B and C when the chain hoist is supporting its rated capacity, okay, and the members are pin joints. Okay. So, the joints are pinned. So, let us solve it. So, what is your first job? As we have promised already, or we have committed to that, my first job is to draw the free body diagram of the whole frame. Okay. My first job is to draw the free body diagram of the whole frame. So, This is the free body diagram, B, D and C. So, this is the reactive force F c and this is the reactive force So, if I say this is my x y, okay. This is given as 3 meter, and this is also given as 3 meter. Okay. Fine. So, this is my free body diagram. Agreed? Now, you may ask me, I am showing FB like that. So, our objective for this problem, our objective is to find out FB and FC. Those are the support reactions. Now, you may ask me, or obviously it is coming to your mind now, that I have shown FB in this direction and FC in horizontal direction. Now, who is telling me to take these directions, right? So, the obvious question is arising in your mind, and the answer is that CD and BD both are two force members, right, because the way this is a frame structure. This is very much similar to your truss system, okay? And the members can be idealized as the two force members. Now, if the members are two force members, say CD as well as BD both are two force members, then the reaction force will be acting along the axis of the member, yes or no? Already we have seen that thing when we are discussing about two force members and three force members like that. At the time we discussed this thing. Now, this FB will be acting along the line BD and FC will be acting along the line CD. Therefore, this FB is inclined with the horizontal and we can resolve this FB force, okay, in two components, Fx and Fy, Fbx and Fby. So, for our convenience, of course, if it is, I mean it is not required, but for our convenience we are taking these components and later on we can take the resultant to find out FB. So, FB is the resultant of Fbx and Fby. Fine. Now, another thing you may ask me, that is also coming to your mind, that I am showing Fc as compressive from left to right, whereas Fb I am showing tensile, right. If you recall whatever we have discussed when we are talking about the truss members, the tension member and compression member. So, Fc is shown as the compressive force, whereas Fb is shown as the tensile force. Now, who is telling me to take Fb as tension and Fc as compression? Nobody is telling me, okay. And as I told you, and do not scratch your head or do not think too much the direction of Fc and Fb. Whatever I have shown from my assumption. Say let us say Fc is compressive, Fb is tension, okay. Now, after the solution, if I get the same, I mean positive value of Fb and Fc, then whatever direction I have considered, that is correct. If they are opposite, then whatever direction I have considered initially, that is wrong, okay. So, we should not think much about the direction or the nature of force, okay. So, now once we have drawn the free body diagram, so this is your free body diagram of the whole frame. Now, what we can consider? So, now we know this whole frame is under equilibrium. So, we can satisfy the equilibrium condition. So, first one we are considering moment equilibrium with respect to point B, moment equilibrium with respect to point B. So, and we are considering clockwise moment as negative and anti-clockwise moment as positive. This is my convention. You can choose different conventions, but you stick to the convention throughout the problem. You do not change your convention in between. Okay. So, this is my convention, clockwise moment is negative and anti-clockwise moment is positive. Okay. So, now if I want to take the moment equilibrium with respect to point B, so what are the forces are causing moments? F c as well as this 20 kilonewton. So, F c is giving me anti-clockwise moment. So, F c multiplied by 3 and this 20 kilonewton is giving me clockwise moment. 20 into 3 is simply 0. So, from here I get 20 kilonewton. Okay. So, F c is obtained. Now, let us talk about, now similarly if you take the moment equilibrium with respect to point C, then basically you will be getting F b x into 3 minus 20 into 3. Once you are taking moment with respect to C, so F c will not be participating. So, F b x into 3 and 20 into 3, this 20 kilonewton will be giving you the moment, and F b y is not giving you any moment because that is passing through point C. Okay. From this you may get F b x equal to 20 kilonewton. Similarly, if you satisfy this condition, summation of F y is 0, then basically from this you will be getting F b y minus 20 is equal to 0. Okay. F b y is in the upward direction, 20 kilonewton is acting downward direction. So, these are two forces only in the y direction. So, from this you will be getting F b y equal to 20 kilonewton. So, therefore, F b I can write simply F b x square. So, that is coming 28.28 kilonewton. So, your support reactions F b equal to 28.28 kilonewton positive, that means whatever direction I considered, that is correct. Similarly, F c I got 20 kilonewton here, that is also positive. So, therefore, whatever direction we considered initially, that is the compression, that is also coming perfect. Now, you can check this problem by taking F c in the opposite direction and F b in the opposite direction, and then you will see these values, numerical values will be coming same, but they will be in the negative value. Okay. So, that will tell you that directions whatever you have considered initially, that is not correct. Fine. So, thank you very much. I will stop here today. So, in the next class we will be taking some more numerical problems to understand this particular chapter. Thank you very much.